Other examples of using integrating factors besides the tank problem that we've just done are not that hard to find. Let's go back and take a look at a few examples we've done in the past and augment them. Recall, for example, Newton's law of cooling. Do you remember that one? That's the one that had the equation dt dt, where capital T is the temperature, is equal to kappa times quantity A minus T, where kappa is the heat transfer coefficient and capital A is the ambient temperature in which that body sits. Now, we've done that in the past, and we solved that just by a simple substitution, because it's an affine equation. And our solution was capital T is quantity T naught, the initial condition, minus A, times e to the minus kappa T plus capital A. And what that means is that the temperature of the body is exponentially moving towards the ambient temperature. That was really nice, really simple. But what happens if that ambient temperature is changing? It's a function of time. We now have a non-autonomous differential equation, an affine differential equation to which our methods apply. So what we're looking at is the differential equation dt dt equals minus kappa t plus kappa times a as a function of time. What's the integrating factor for this? Capital I is equal to exponentiating the integral of kappa dt. Since kappa is a constant, this is simply e to the kappa t. If we now go back and recall what our final solution looks like when we have that integrating factor I, we can substitute in e to the kappa t and get a final answer of temperature, capital T, is e to the minus kappa t times the integral of e to the kappa t times kappa times a of t dt. Wait, so what's that turn out to be? Well, it depends. That general solution is maybe not so easy to compute yet. It depends on what the form of capital A is. So, for example, let's consider what happens when the ambient temperature is fluctuating. Let's say that we've got something like, a swimming pool, and that swimming pool has some temperature, but the ambient temperature that it sits in goes up and down and up and down and up and down every day, as it's warmer in the daytime and cooler at night. We might model that, in this case, by saying, capital A could be sine of t. Maybe we'd want some more constants in there, but let's just keep it simple. In this case, the final solution for the temperature of the pool would be e to the minus kappa t times the integral of e to the kappa t times kappa sine of t dt. So I really have to integrate an exponential function times a sine. And we don't know how to do that. I know how to do that, but we don't know how to do that yet. Are we going to learn how to do that? Yes, we will. We will take it on part by part. But at this time, shrug emoji, this is kind of an unknown. We don't know how to integrate functions like that yet. So let's move on. And let us once again go back to a different affine differential equation. This time, linear drag, where the equation in question was m times dv dt, where v is the velocity of a body. That was equal to mg minus kappa v. Of course, m is the mass, g is the gravitational constant, and kappa is the linear drag coefficient. Now, just like before, our solution to this affine ODE was obtained via substitution, and we got v is equal to quantity v naught minus mg over kappa times e to the minus kappa t over m plus mg over kappa. That means that you are exponentially converging towards this constant mg over kappa, which is the terminal velocity for this falling body. Remember that, okay? Okay. Because all of this assumed that everything in sight was constant. The mass, the gravity, the drag coefficient, all constants. But what happens if these things are changing? Let's say the mass is changing as a function of time, or the drag coefficient. Well, let's do it. Let's write down the most general possible affine equation. That would be of the form dv dt equals minus kappa of t divided by m of t times v plus g of t. This is an affine non-autonomous differential equation. We could do this if we can compute an integrating factor. To get that integrating factor, capital I of t, what we have to do is exponentiate the integral of kappa of t divided by m of t dt. So depending on what the form is, if you can integrate that, and if you can integrate the resulting solution, well, maybe you can do something. What would be a good example in this case? Oh, I've got it. Let's say that we're looking at a hailstone that as it's falling is picking up more mass from the ambient water vapor. So it's falling and it's getting bigger and bigger and bigger. The mass is changing. Let's say that that mass is modeled as c times t for some positive constant c. Let's keep gravitation a constant, the drag coefficient a constant. This gives us a differential equation, dv dt equals minus kappa over ct times v plus g. Now we can solve this with an integrating factor. The integrating factor for this equation, capital I of t, is the exponential of the integral of kappa over m dt. But m is c times t, so what do? I can pull out that kappa over c, and then I have the integral of dt over t. That gives me log of t. And exponentiating a log, that's going to turn out to be really nice. E to the log of t is just t, but I've got that kappa over c out in front that converts into a power. So our integrating factor, capital I, is t to the kappa over c. Thinking back to what the final solution looks like, when you have an integrating factor, I, we can substitute in and get a final answer. V is t to the minus kappa over c times the integral of t to the kappa over c times g dt. That's a simple integral. Pull out the constant, do a little bit of work to simplify everything in sight, and what we get is the initial condition, v naught, plus cg divided by c plus kappa times t to the power c plus kappa over c. And that's it. We're done. That's the velocity. And that's so interesting because in this case, what we have is polynomial growth in the velocity, depending on these coefficients. We do not have exponential decay towards a terminal velocity. That hailstone just keeps dropping faster and faster. That's kind of interesting. A little bit scary if you're in a hailstorm, but that's the way that things look, subject to the assumptions of the equation. It's a really interesting example. Are there more examples that we could do? Absolutely. There are lots of interesting affine equations for population models, for drug dispersal within the human body, all kinds of things that you can model in this way where integrating factors are helpful. But that's just one technique. This is just the beginning. Now we need to wrap things up, but it's bonus time! There are so many classes of difficult differential equations that we could be considering. The methods that we're going to learn, the methods that we've already learned, they're going to fail for most interesting differential equations. But the equations themselves are worth knowing about. You may want to check out the following families of differential equations, everything from A to Z, from Abel to Bernoulli to Bessel to Euler, Exact, Fuchsian, Legendre, Leonard, Painlevé, all these French guys, Riccardi, Van der Pol, they're not French, etc., etc. It goes on and on. There are so many interesting examples.